Yes, hello everyone. Welcome to our channel. Yes, today we are going to discuss one very important topic of probability and statistics, unit 1. Right, we are going to our topic, that is Bayes theorem. Bayes theorem on probability. So let us first look our statement of Bayes theorem. So if E1, E2 up to so on En are n disjoint events in a sample space S, and capital A is another event in S such that A is contained in union of I equal to 1 to n Ei, then P of Ei given A equal to P of A given Ei into P of Ei by sigma I is equals to 1 to n P of A given Ei into P of Ei. Let us see what is the meaning of this statement. Say here what is given: E1, E2, E3 up to so on En are n disjoint events. Disjoint events are nothing but the intersection of the events is equals to pi. Clear? All we know according to the set theory, if any two events are disjoint, that means the intersection of the events is equals to pi. Clear? So we have taken here, if you observe this diagram, we have taken E1, E2, E3. This is the sample space. Total, this square bracket represents the sample space of a random experiment. And these are the events E1, E2, E3 up to so on En are n mutually disjoint events. Disjoint means E1 intersection E2 is equals to pi. So this is an event and this is also an event, but the intersection of these two events is equals to pi. Clearly you observe this. E2 intersection E3 is also equals to pi. Like that, for any two events, the intersection is equals to pi. Clear? Then what is given? A is an event such that it contains union of E1 to En. That means some part of A, some part of A. So this is the total A. Some part of A must contain in E1, some part of A must contain in E2, some part of A must contain in E3, so on some part of A must contain in En. This is the meaning of A is contained in union of I is equals to 1 to n Ei. Okay. So A is an event such that A is an other event such that which contains all the union of E1 to En. Okay, clear? Okay, now if we observe A intersection E1, that means some part of A contains in E1. Therefore, there is obviously intersection part of A and E1 exist. And there is obviously intersection part of A and E2 exist. There is obviously intersection part of A and E3 exist. Like that, there is obviously intersection part of A and En exist. Okay. So this is the meaning of A contains in E1 to En. Then if we clearly observe, if A is an event in the total events, and if we take A intersection any two intersection of any two events of E1 and E2. Say for example, I am taking A intersection E1 intersection E2. What will happen? Yes. So because A intersection E1 intersection E2, E1 intersection E2 is pi. Clearly we know that. So A intersection pi. A intersection pi is equals to what? Pi, obviously. Clear? So A intersection pi is equal to pi. That means if we take intersection A intersection of any two intersections of E1 and En, we will get it as pi. Clear? So that's what we have explained in the next slide. So clearly you observe here A intersection E1 exists, but A intersection E1 intersection E2 is equals to pi. That means A intersection E1 intersection A intersection E2. All these are mutually A intersection E1 intersection A intersection E2 is equals to pi. So I think you understand it. Because A intersection E1 intersection A intersection E2, we can write it as A intersection of E1 intersection E2. Clear? So A intersection of E1 intersection E2 is equal to A intersection E1 intersection A intersection E2, that is going to be pi. Therefore, all A intersection E1 and A intersection E2 up to so on, these all events are okay mutually disjoint events, as like E1, E2, E3 up to so on En. These also, if I take A intersection E1 is another event, say capital some P1, and A intersection E2 is equal to say capital P2. All these events are also mutually disjoint events. Clear? Okay. Then we move to the next slide. So see here, so that's what exactly we have written here. Let E1, E2, E3 up to so on, En, Bn disjoint events in the sample spaces which is given in the statement. A is another event in S such that A is contained of I is equal to 1 to n Ei union of E1, E2, E3 up to so on En, which is given in the statement. Ei's are disjoint, that means Ei intersection Ej, what we have explained, what we have discussed just now. That is what here in generalized form, Ei intersection Ej equals to pi. In the place of I, you can take any value 1 to n. In the place of j, you can take any value 1 to n, but both are not equal. Because what happens if both are equal, even and even, that is equal to even. Okay. So if I take I is equal to 1, I am taking j is equal to other than 1, E1 intersection E2 or E1 intersection E3 or E1 intersection E4, so on. Whatever we take, that is going to be pi. And I am taking any two events intersection with A. Okay, A intersection Ei intersection A intersection Ez. That is what we have discussed just now in the previous slide. That is going to also be pi for I not equal to j. Is it clear? So I am taking now A is equals to. Now I am taking A is equals to. Why I am taking A is equals to? Because I need to find P of Ei given A. So previously you need to know the conditional probability statement. P of Ei intersection A is equals to, because in the Bayes theorem, what is the LHS part? P of Ei given A. So according to the conditional probability, P of Ei given A is equals to, I think all you know the conditional probability. So according to the conditional probability, P of Ei given A is equals to P of Ei intersection A by P of A. Clear? P of Ei intersection A by P of A. So that we need to find P of A in the denominator. Clear? We need to find P of A in the denominator. What is in the numerator? P of Ei intersection A. What we know clearly? P of Ei value no. Because and that means E1, E2, E3 up to so on En all are given sets. Clear? E1, E2, E3 all are given sets. That means we clearly know that even probability. So in the numerator I can write it as P of E1. Say for example, if I take in generalized form Ei, if I know ith event probability, because this is given set. So Ei intersection A, according to the conditional probability, we can write Ei intersection A, because I know that Ei. Therefore, in the given part, we must get Ei. So what I need to get, what I get in the numerator part? A. Clear? So that this is the numerator part of the Bayes theorem. Clear? So this is very simple, because we know that the given set probability Ei. So we are writing P of Ei intersection A as P of Ei into already we have P of EI, therefore EI must be exist in the given part, P of A given EI. This is the numerator part. And what is the denominator part? According to the conditional probability in the denominator part, this is A. Therefore, according to the conditional probability, P of A must be there in the denominator part. Clear? So that we need to find P of A. P of A, the probability of A, here we need to write, that is the important part in Bayes theorem. So for that I am writing A here. So how do I write A here? A is equals to, I am writing A intersection E1 union A intersection E2 union so on A intersection En. So some may get a doubt, how do we get A intersection E1 union A intersection E2 union so on A intersection En. So for that I am writing one more step here. So please observe carefully. Uh, okay, is it visible? Yes. So I am writing A is equals to A is equals to A is equals to A intersection S. Clear? So obviously S is the sample space, A is the set contained in S. Therefore A intersection S obviously is equals to A only. Clear? So this is going to be A intersection yes. How do I write yes? Yes can be written as E1 union, because E1, E2, E3 up to son En are mutually exhaustive and exclusive events. Exhaustive means E1 union E2 union E2. This is not visible, I think. We will write with another color. Okay. Right. Okay, I am writing here A is equal to A intersection S. So that is equals to A intersection A intersection A intersection S is going to be E1 union E2 union E3 union E4 so on so on so on En. So now we can use distributive property. What is distributive property? If in the bracket term uh, intersection is there, so in the open part in the open part intersection is there, and in the bracket part union is there. So you can write it as intersection E1 union intersection E2 union intersection E3 union so on. So what that's what we have written here. A is equal to A intersection E1 A intersection A A intersection E1 union A intersection E1 union and A A intersection E2 A intersection E2 union A intersection E3 so on A union A intersection En. So clear? Is it clear? So you can write A is equal to A intersection E1 union A intersection E2 union so on A intersection En. If you observe the diagram also, you can easily find out A intersection E1 union A intersection E2 union so on A intersection En is equal to A. If you write this, the half of the theorem is over. Now applying the probabilities on both sides. P of A is equals to P of A intersection E1 union A intersection E2 union so on A intersection En. Now what is going to be the according to the additive axiom, because all these events are mutually, yes, disjoint events, because A intersection E1 intersection A intersection E is equals to pi. Therefore, in the place of union, according to the additive axiom of the probability, in the place of union, we can replace with plus sign. Okay, P of A is equals to P of A intersection E1 plus P of A intersection E2, so on, plus P of A intersection En. So, in the sigma notation, because all these events are up to so on n, we can use sigma notation. I is equal to 1 to n P of A intersection Ei. Clear? Up to this step, I think you make clear. Okay. Now P of A is equals to P of A is equals to sigma I is equal to 1 to n P of A given Ei. P of A is equal to P of A intersection A. According to the conditional probability, we can write it as P of A given Ei into P of A, because we know the event Ej probability, Ei probability we know clearly. So that we are writing P of Ei into P of A given Ei. When we write P of Ei, according to the conditional probability, Ei must be in the denominator. Okay, P of Ei. Why we are writing like this? We only know Ei probability only. Already E1, E2, E3 are given sets. So those are given sets. Therefore, P of Ei into P of A given Ei. This union, the union of E1, E2 up to so on En also equal to sample space. That means each and every event probability we know clearly. That means those are the given probabilities. So that we are writing P of Ei. Clear? Is it clear, all of you? So why we can write P of A given Ei in the A intersection Ei in terms of P of Ei means we clearly know the probability of Ei. That's why we are writing P of Ei here. Okay. So sir, somebody may doubt, sir, how why we can't write P of A, because we know we are finding A probability only. So you can't write P of A here. Clear? Is it understand? Right, yes. P of Ei into P of A given Ei. This is what the probability of A. Okay. Now by conditional probability, we can write P of Ei given A is equals to P of Ei intersection A by P of A. Okay. P of Ei intersection A, how can we write P of Ei? Because we know that Ei probability. So P of Ei into P of A given Ei by P of A. So already we have found P of A. So we substituting here P of A. Okay. Is it clear, all of you? This is what Bayes theorem. Now we are going to discuss some problems on Bayes theorem. So these are very important problems on Bayes theorem. So we will discuss two problems on Bayes theorem. In certain college, 25% of boys and 10% of girls are studying mathematics. The girls constitute 60% of the student body. The first question is, what is the probability that mathematics is being studied? And the second question is, if a student is selected at random and is found to be studying mathematics, find the probability that the student is a girl and a boy. Okay, we will see it. So here I have written the question again. In a certain college, 25% of boys in a certain college, 25% 25% of boys and 10% girls are studying mathematics. The girls constitute 60% of the student body. What is the probability that mathematics is being studied? And second question, if a student is selected at random and is found to be studying mathematics, find the probability that the student is a girl or a boy. So if we observe the carefully, is this problem belongs to Bayes theorem or not? First of all, we need to understand that. So to understand that, so what is the given data here? Clearly, 25% of the boys and 10% of the girls are studying mathematics. Okay. Out of 60% of the girls in the student body. So that means particularly in the college, 60% of the girls and 40%. If 60% are girls, How many boys are there? 40%. Clear? Because total 100%. So 60% of girls and 40% of boys are there in the college. Among 60% of the girls, 10% of girls are studying mathematics. Clear? So the girl student who are studying mathematics, the girl student who are studying mathematics is given clearly. The girl student G by who are studying mathematics, G by M is given. Clear? So like this you need to understand, is it conditional probability or not, and applicable Bayes theorem or not. So the girls student who are studying mathematics is given, as well as the boys student who are studying mathematics is given. That means P of G by M is given, as well as P of G is given, because 60% of the students, girl students, total girl students probability is given, and P of B by M by B is also given. Boys students who are studying mathematics is also given 25%. That means P of M by B is given, P of M by G is given. Clear? That means what is the probability that total mathematics being studied? So we can study, we can find total probability of studying mathematics P of M. And the second question is, if a student selected at random is found to be studying mathematics, if he is studying mathematics, find the probability that student is a girl. So we need to find P of G by M. P of M by G is given. P of G by M we need to find. That means it belongs to the Bayes theorem. Clear? So like this we need to understand. Now coming to the solution. So B is equals to the event of selecting a boy, G is equals to the event of selecting a girl, M is equal to the event that the student is studying mathematics. Clear? Now given that probability of selecting a boy, so P of B is equals to 40 by 100. How do we get 40 by 100? Because in the total strength 60% of the students are girls. That means remaining percentage of the students are boys, obviously. So P of B is equals to 40 by 100. And the probability of selecting a girl, obviously it is given in the problem only 60%. So P of G is equals to 60 by 100. And probability that mathematics is studied, given that is probability of mathematics is studied given that student is a boy. So if the student is a boy and the probability of he studies mathematics is given as 25%, that is 25 by 100, that is going to be 1 by 4. And the probability of a girl who studies mathematics is 10%, is given in the problem only, 10 by 100, that is equal to 1 by 10. Up to this is clear? Yes. Now we go into the next slide. Now what we need to find, what is the probability that mathematics is being studied? What is the probability that mathematics is being studied? So how do we find it? What is the probability that mathematics is being studied means P of M we need to find. So P of M, how can we find? P of M is equals to, yes, exactly. So if we take or if we select a girl, if we select girl, that girl should be studying mathematics. Okay, selecting a girl, selecting a girl, sorry, my mouse struck. Yeah, so we select a girl. If we select a girl, she should be studying mathematics. P of G into P of M by G. That means this is clearly the event A in our Bayes theorem statement. Plus, because there are some boys, so if we select a boy, so if you, I think if you observe the problem, clearly the basic events are G and B, isn't it? The basic events are in the Bayes theorem E1, E2, E3. As like E1, E2, E3, here the basic events are probability of B and probability of G. And the event A is here M. Okay, in the Bayes theorem as like A, here M, the studying of mathematics. Clear? P of B. If we select a boy, he should study mathematics. P of M by B. Okay, this is how we find a student who study mathematics, right? So all we know in this formula, P of G, we know that is given. P of G is equal to 60 by 100. P of M by G, P of M by G, we have 1 by 10, that is also given in the problem, plus P of B, P of B is given 40 by 100, and P of M by B is also given. If we substitute all these values in this, we will get the answer, the probability of that mathematics is being studied. Now the next question is, if a student is selected at random and is found to be studying mathematics, find the probability that student is a girl. That means what we need to find? We need to find the probability if we select a student randomly, that student is a girl, that student is a girl. Find the probability random to be studying mathematics. Okay, if we select a student randomly that he is studying mathematics, that student must be a girl. What is the probability that the student is a girl? We need to find this probability. Okay, P of G by M. So P of G by M, how do we find P of G by M? Clearly the basic event is here G only. Clear? The basic event is G. So we can write P of G by M as G intersection M by, according to the conditional probability. Here we can apply the Bayes theorem. So P of G intersection M by P of M. Already we found P of M. Then how do we find P of G intersection M? What is the basic event here? P of G. We clearly know in the given data, P of G into when we write P of G, it should be in the denominator in the product part. So P of M by G, P of M by G whole by P of M. So all the values we have. Clear? Now by substituting all the values in this, we will get the answer. So that is what we can find here. Probability that maths being studied is P of M is equal to, just now we have discussed it, P of G into P of M by G plus P of B into P of M by B. Therefore, substituting the values, we are getting the answer 4 by 25. You can calculate it by using calci. So the by Bayes theorem, probability of mathematics student is a girl, P of G by M. Okay, probability mathematics student. If we select a student randomly and we know that the student is studying mathematics, and what is the probability that student is a girl? So P of G by M. So P of G by M is equals to P of G into this is extra, P of G into P of M by G by P of M, and substituting we will get the answer. Like that we will get P of Y by M also. Okay, is it clear all of you? I think it is clear all of you. So like that you can do this problem also. So the previous problem is depends on two events, only boy and girl, and some problems may contain more than two events. If more than two events also, you can do like this only. In a bold factory, machines ABC manufacture 20%, 30% and 50% of the total of their output, and 6%, 3% and 2% are defective. A bolt is drawn at random and found to be defective. Find the probabilities that it is manufactured from the mission A, mission B and mission C. So here we will take P of A, P of B, P of C denote the probabilities of the events bolts manufactured by the machines A, B, C. So here basic events are clearly 20%. A company manufacturing 20% of the bolts, B company or factory manufacturing 30% of the bolts, and C factory manufacturing 50% of the bolts. These are the basic events. If we add these three events, we will get it as 100%. So the probability of manufacturing bolts by A company is P of A, that is 20%, that is going to be 20 by 100, and the probability of manufacturing bolts by the company B is denoted by P of B, that is going to be 30 by 100, and the probability of manufacturing bolts by the company C, that is going to be P of C, that is equal to 50 by 100. Clear? Now there is a defect in bolts manufacturing by the company A is 6%. That means defective bolts from the company A. Defective bolts from the company A. If A manufacture bolts, the defective bolts are 6%. So defective bolts in the company A is 66 by 100. Defective bolts, that means this D is nothing but uh, our event defective, as like capital A in our Bayes theorem. Okay, what is the total defective probability? We will find it. So P of D by A, P of D by B, P of D by C is given. This is, so first we can find P of D. So what is the, if a bolt is selected, then what is the probability that it is defective if it is asked in the question, but it is not asked in the question, but we need to find it by for finding these values. Okay, the defective probability means if we select bolt from factory A, it must be, it may be defective, so P of A into P of defective bolt from the factory A, vice versa applicable for B and C also. So this is the defective bolt probability. Clear? Now we need to find if we select randomly, find the probabilities that it is manufactured. A bolt is done. A bolt is done randomly. So if a bolt is done randomly, then what is the probability it is defective from the factory A? Okay, what we need to find? P of A by D. Okay, we have drawn a defective bolt, but what is the probability it is coming from factory A? Okay, P of A by D we need to find. So P of A by D is equal to P of A intersection D, P of A intersection D by P of D. P of A intersection D by P of D. First we write like this, because if it is asked for 10 marks, you need to write like this. Clear? P of A intersection D by P of D. What is P of A intersection D according to the conditional probability? All we know that P of A. This is the basic event P of A. P of A we know that P of A. So if we write P of A, then A should be in the denominator, P of D by A by total probability. Clear? Then substituting the values, we will get the answer. So likewise, we can find P of B by D. So P of B by D means the basic event is P of B, and P of D by B by total probability. We can find. Okay. So this is what the problems on Bayes theorem, right? So hope all of you understand Bayes theorem and the problems on Bayes theorem. So I'm going to leave now. We'll discuss one more topic in the next class. Thank you. Thank you very much.